After discussing processes in Chapter 3, we will skip over threads in Chapter 4 and process synchronization in Chapter 5, and we will continue with Chapter 6 on CPU scheduling, the scheduling of basic processes. After finishing this chapter, we will go back to Chapter 4 on threads and then to process synchronization. So in this chapter, we will first discuss the criteria used for scheduling. Then we will discuss some alternative scheduling algorithms based on these criteria. Then we will skip the sections on thread scheduling and multiprocessor scheduling, which are actually moved to Chapter 4 in our outline. And then continue with real-time CPU scheduling and some examples of operating systems. We will finally discuss how we can evaluate algorithms to decide which algorithm is better for our use. So our objectives in this chapter are as follows. First, we will be discussing CPU scheduling for the multi-programming operating systems. That means we have several processes. Typically, most of these processes would be for an interactive system. We will also describe some different CPU scheduling algorithms and see how we can pick the correct algorithm for our needs for the operating system we have in mind. And we will also examine the scheduling algorithms of several operating systems. So, if we consider an operating system in a multi-programming environment, especially if these processes are interactive processes, they will constitute of some chunk of instructions that will be executed in the CPU, then some I/O, again some instructions, again I/O, again instructions, and it will just continue this way, switching between what we call a CPU burst, which is that chunk of instructions, followed by an I/O burst, where you do I/O, then again instructions in a CPU burst, I/O burst, CPU burst in the cycle. A process will always start with a CPU burst because in the very beginning, at least you have to start the main function. So still there are some instructions that are being executed to start the main function. And also at the very end, at least you have to exit the main function. You return a value from the main function. Therefore, there will always be a CPU burst also at the end. And in the middle, you will always switch between these CPU bursts and I/O bursts. Remember that one of our primary goals is to keep the CPU busy, and also keep in mind that the CPU is much faster compared to the I/O devices. So we will try to do context switches to keep the CPU and actually also the I/O devices as busy as possible. We don't want to waste these valuable resources. So if you look at the length of the CPU bursts, sometimes the CPU bursts will be quite short, but sometimes they will be quite long. So how likely is it that the CPU bursts we observe are short or long? If we take the histogram of the CPU burst times, that means check how frequently we have short CPU bursts of medium length, and long CPU bursts. If we plot this in a histogram where the x-axis is the duration of the burst, typically in milliseconds, and the y-axis is the frequency of observing CPU bursts of this length, we see that most of the CPU bursts are quite short, and as the burst size increases, the frequency of observing such bursts is almost negligible. So this gives us actually some idea. Keep in mind that typically our CPU bursts are quite short. Okay, that's important. But this is, by the way, the case for interactive systems. So the CPU scheduler, remember we also call that the short-term scheduler, is now a scheduler that looks at the processes that are in the system, in the memory at that very moment, and decides who gets into the CPU and which processes are going to wait in the ready queue for their turn. Note that in this chapter, unless we mention otherwise, when we talk about CPU scheduling, we talk about a system with a single CPU that has a single core in it. And also our processes do not have threads. So every process, in other words, is composed of a single thread. Okay. So now we have a queue of processes that want to go into the CPU, and the CPU scheduler actually decides how you manage that queue, who goes next in that queue. So the CPU scheduling makes its decision in the following 4 cases. One case is when you're switching from a process is switching from the running state to the waiting state. Well, when does that happen? If it's in the running state, that means the process is in the CPU, it's running at the moment, and it switches to the waiting state, remember, when it tries to do some I/O, when it is waiting for an event. Okay? So when you want to do I/O, a scheduling decision should be taken. Or if the process is again running in the CPU, but the time slot you have assigned to that process has expired, that means the process has been in the CPU for too long, to allow for the other processes to take their turn, you put this process out of the CPU, but put where? You cannot put it in the waiting queue because actually the process did not try to do I/O. The process actually should be scheduled when the CPU becomes available. Therefore, you put that process back in the ready queue, so its state also changes to the ready state from the running state. Or an alternative case where we need to make a scheduling decision is when the process switches from the waiting state to the ready state. Now, when does that happen? If the process is in the waiting state, that means earlier it had requested some I/O operation. That I/O operation was hopefully started, and the I/O operation completed. Therefore, an interrupt has been raised by that I/O device to the CPU saying something happened, and the CPU handles that interrupt to see what that interrupt is. Okay, that's an I/O operation completion. So which process was waiting for this event? Say process P1 was waiting for this event. So process P1, which was in the waiting state, can now proceed, okay? But some other process was already executing when this interrupt occurred. So we do not suddenly switch to process P1 because its I/O has completed, because some other process was already in the CPU and we have still in its time to handle this interrupt. So the operating system typically puts the process for which the I/O operation was completed, in this case P1, to the ready queue, so that now when the CPU becomes available, this process may now continue because it's not waiting for I/O anymore. And typically the CPU will be returned back to the process which was interrupted. And finally, last case is the termination of the process. Well, if the process ends, even if its time slot is not over, you just need to do a new scheduling. You should give a new scheduling decision because there's nothing to execute at the moment. We don't want to keep the CPU just idle. Among these 4 cases, the first one and the last one are said to be non-preemptive. So first let's discuss what preemptive means. Preemptive means although a process was in the CPU and it did not want to leave the CPU by itself, either by making an I/O request or termination, it should be removed from the CPU. So such a case is what we call the preemptive case. In the cases of 1 and 4, the process gets out of the CPU because it's willing to do so. That's why it's non-preemptive. But if you look at the other two cases, cases 2 and 3, the process is forcefully removed from the CPU. Remember, in case 2, the process wanted to continue in the CPU, but its time was over. So you preempt that process from the CPU. And in case 3, the process again wanted to continue, but the I/O operation of another process was completed. Therefore, at least temporarily, the process was removed from the CPU. In other words, it was preempted from the CPU on behalf of another process. So those two, cases 2 and 3, are preemptive, and cases 1 and 4 are non-preemptive cases. So the preemptive cases occur when you consider access to some, for example, shared data, or consider preemption while you're in the kernel mode, or you should also consider the interrupts occurring during some crucial OS activities. These should be taken into account when you have some kind of preemption. Okay, because, for example, if you're making use of some shared data and the process gets kicked out of the CPU, it becomes preempted, then you should preserve the integrity of the shared data. Or if the process had made a system call, so it was in the kernel mode, but still that process is executing, now not in the user mode, but in the kernel mode, and then you decide for a preemption. If the CPU remains in the kernel mode and the new process starts, if it finds the CPU in the kernel mode while it's executing the regular instructions, that's a big trouble. Okay, that's a severe security concern. So you should also take care of that. You should consider that. And the last thing you should consider is the operating system was doing something crucial, something not to be actually interrupted. So if an interrupt occurs at that very moment, you should consider how you handle such a case. Now, the scheduler just makes the decision. It says, okay, P1 is the next process to be executed, but somebody should do it for you, okay? P1 cannot do it by itself because it's not even executing any instructions. It's completely out of the CPU. A process outside the CPU cannot move itself into the CPU, because to do that, actually, you need the CPU itself, okay? So there is a function of the operating system called the dispatcher, which executes or implements the decisions made by the scheduler. So again, the scheduler makes the decision, and the dispatcher applies that decision, realizes that decision. How? It needs to do what we call context switching. The process, say you want to switch from process P1 to P2, okay? P1 is currently in the CPU, so it has some important values in the registers. We should remember those values, because when we return back to P1, we should continue with the case from the moment that those values, exactly those values, were in those specific registers. Otherwise, you would be continuing from a different state. Okay? So to save the state of the process that is to be preempted from the CPU, you should save the values of all registers, the general purpose registers, but also the special purpose registers, like the program counter, the instruction register, accumulator, whatever, all of them, the stack pointer and others. And for the other process, P2, which is supposed to come into the CPU, now you should restore those values. And where these values are stored when the process is kicked out of the CPU, these values are stored in what we call the process control block, PCB. That's why we have the PCB actually. You should, doing this operation, doing the context switch, is something to be done by the operating system. You should not let ordinary programs, processes, be able to do this, because this would violate all your scheduling decisions. Therefore, they should be executed in what we call the kernel mode. Now, to do the context switch, you switch from the user mode, in which the regular process instructions were executing, and now the operating system takes over. It does the context switch by, again, saving the state of the current process and restoring the state of the new process to come into the CPU. And then, before returning the control back to that process, that new process, it has to return back to the user mode. You should not forget that. Again, you should not stay in the kernel mode for that. And you should also jump to the proper location of that new process that comes into the CPU. And to be able to do that, actually, you should be restoring the value of the program counter. That's why we store the program counter in the PCB. Now, all this operation takes time. This is done by the dispatcher, and the latency, the delay introduced by this dispatching operation is called the dispatch latency. Note that this is some overhead. During the dispatching operation, you're not doing any useful work. Actually, you're not executing any instruction of any process. You're just doing operating system overhead to manage the system properly. So this overhead should have a low percentage in all the CPU time that's used. So if you look at the CPU time that's used in the system, some of it is for the overhead due to dispatcher, and the rest should be normally for the processes that do the useful work. And we would like to diminish the ratio of this dispatch latency. So that means the dispatcher should be quite simple, and it should be very fast, so that we have low dispatch latency. So when we design a scheduling algorithm, what kind of criteria should we look at? What is important for us? Actually, we have several criteria. The first one is, we have always mentioned this, we would like to have higher CPU utilization, okay? Because we want to keep the CPU as busy as possible, because that's the one that's executing the instructions. In parallel with this, actually, you will also have a concept, what we call the throughput, which is the number of processes that are completed in some given time unit. Whatever that time unit is, it could be minutes, it could be hours, or it could be seconds, whatever. That's not important, but it should be fixed. Let's say in minutes. So how many processes are completed, say, in a minute? The turnaround time is the amount of time for a process to execute. That means you start the process by double-clicking the icon, or typing the name of the program at the command prompt, or whatever. Somehow you start the process, and you start your timer, and you stop your timer when that process ends, and look at how much time it has taken. Well, that time, of course, depends on what that process is doing. So if it's a simple process, you would expect it to end in a short time. But if it's a very complex process, of course it would take time. However, the turnaround time is not only the time the process spends in the CPU. It also spends a lot of time in the waiting queue, depending on the type of I/O it's doing. And more important, it also spends some time in the ready queue, because it was actually ready to execute. It was ready to go to the CPU, but the CPU was assigned to other processes. So the process did not have the time to go to the CPU. So turnaround time, once again, is from the moment you start the process until the moment the process ends. All the time is our turnaround time. The waiting time now is the time that process was actually waiting in the ready queue. Pay attention, we're specifically mentioning the ready queue, not the wait queues in waiting time. So if you actually subtract the waiting time from the turnaround time, you would end up with the time the process spends in the CPU plus waiting for I/O operations. And the response time is the amount of time that's taken from the moment you start the process until the first response produced. Okay? Now, this is different from actually the turnaround time. The turnaround time is from the beginning of the program to the end of the program. This time, in the case of response time, it's again from the beginning of the process, but until the first response. Okay? Now we want this first response to be as short as possible if you're talking about time sharing systems, if you're talking about interactive systems, because this is actually your interaction, that first response. Okay? If the first response is too late, then for the human user, it appears like the system is not responsive. Okay, you start the program and you just sit and wait until something happens. Okay, therefore we need some short response time. Now, if you look at all these criteria, how do we use this criteria when designing an operating system? Do we want to maximize them or minimize them? How do we do that? Well, you should try to maximize CPU utilization because you would like to keep the CPU as busy as possible. You should also try to maximize the throughput so that you get more processes completed in a given time. But you should try to minimize the turnaround time, the time from the beginning to the end. Of course, you should also try to minimize the time spent in the ready queue because it's just wasted time. And also, you would like to minimize the response time so that the system becomes more responsive. Unfortunately, these criteria are typically contradicting with each other. For example, to minimize the turnaround time, I could do the following. I accept only one process to the system, okay? So since there are no other processes, that process will be completed in the minimum time that's possible, okay? Therefore, the turnaround time couldn't be shorter because I've dedicated all resources only to that process. That's the optimal answer. However, in that case, most of the time the CPU would be sitting idle because when the process wants to do I/O, the CPU has nothing to do. It has to wait until the CPU becomes until the process has completed I/O and now wants to execute instructions again. Similarly, the throughput would be at minimum because in the given time, you could at most finish one process because there's only one process in the system. Now, that's a trivial example, but this shows actually one extreme scenario. Okay, perfect turnaround time, minimum waiting time, and minimum response time. Those would be the optimal values, but the CPU utilization and the throughput would be the worst possible cases. Okay. Or at the other end, you can try to put as many processes as possible into the system. Okay. In that case, the CPU, whenever a process wants to do I/O, you will always find a process that wants to use the CPU because there are so many processes. So CPU utilization would be maximized. When the process is complete, the uh, since you're keeping the CPU always busy, it's likely that some processes will be complete. So throughput will also be increased. I'm not saying maximized. Maybe it's not maximized, but at least it would be increased. However, the turnaround time would be diminished because actually it would be too large because always other processes are executing. Similarly, for that reason, you would be waiting in the ready queue a lot because some other processes in the CPU. So waiting time would also increase. And the response time would also increase because you wouldn't get the response immediately due to the reasons we mentioned. Therefore, that's yet another end. So there is a trade-off between the utilization and throughput versus turnaround time, waiting time, and response time. Okay, so we would like to find scheduling algorithms that balance these. Okay.